Hi everyone. Today we're going to look at probabilities with two or more activities. So there's a way to do probabilities with two activities, and then there's a way to do probabilities with one activity. We spoke about these in the previous videos, but let's revisit this idea one more time. A six-sided die is tossed. What is the probability that the number is at least 2? Well, at least 2 implies that the number can equal 2 or be greater than 2. So we could have a 2, 3, 4, 5, or 6, and that probability would be 5 out of 6. If we toss a fair coin, the probability of heads is 1/2. Now notice that tossing a die is one event, and tossing a coin is one event. But when we put these two together, in number 2, if we toss a six-sided die and a coin, let's list the elements in the sample space. In other words, down all the outcomes. So let's just put that in black. Could have a head and a 1, a head and a 2, a head and a 3, a head and a 4, and a head and a 5, head and 6. And then we could have tail and 1, tail 2, tail 3, tail 4, tail 5, and tail 6. And notice I'm assuming here that the coin is first and then the die. So coin and then die. It really doesn't matter which order, but let's agree on that. So the probability that the number is at least 2 and heads. Okay, notice this word and. So we want a number 2 or more and a heads on the coin. Well, if we circle those, we have these. And there are a total of 12 outcomes, and using the counting principle, we know that there are 2 ways the coin could land and 6 ways the die could land, so that makes a total of 12 ways. Here are the outcomes, the sample space. And of those 12 ways, they are all equally likely, so each of these outcomes have a probability of 1/12. But if we have 5 outcomes that we're interested in, the answer is 5/12. Now the question is, how could we have gotten the 5/12 without listing the outcome set? I deliberately made this outcome set easy to list. Well, we know that the probability that the number is at least 2 is a 5/6 by part A, if we treat that as a separate event. And the probability of landing heads on a toss of a coin is 1/2. We got those answers in number 1, A, B. So it appears that if we multiply the 2, we would get our 5/12. And this is the counting principle for probability. And the counting principle for probability says that if 2 events are independent, because the way the die lands and the way the coin lands have nothing to do with each other. They're totally 2 independent experiments. Then the probability that something occurs in succession is found by multiplying their probabilities. So let's write that down on the next page. And notice the key word and. So if we have and with 2 independent events, then we multiply their individual probabilities. Okay, so let's look at this one. I wrote the counting principle of probability for you on this page. And it says, in words, if 2 events are independent, meaning that they do not influence each other, the probability that these events will occur one after the other or in succession is found by multiplying the probabilities. Or we could say if A and B are two independent events, like tossing a coin and tossing the die, then the probability of A and B and then B, or they could occur at the same time, because we could toss a die and a coin at the same time, can be found by taking the probability of A, taking the probability of B, and multiplying them. Okay, so let's take a look at a few problems that you have on your worksheet. Let's take a look at problem number 2 on the worksheet. A jar has 4 white marbles, 2 blue marbles, all the same size. A marble is drawn, put back in the jar, and another marble is drawn. Find the following probabilities. So, if we could just imagine this, we've got a jar. Okay, let's just make sure I could draw this here. So we've got a jar. Here's the jar. And we've got 4 white and 2 blue marbles. All right. Now, we could make a picture of the sample space, and a tree diagram would work beautifully here. So let's make a tree diagram. So we're going to pick the first marble. Now the first marble will either be blue or white. Now if the first marble is blue or white, we pick another, we put that marble back and we pick another marble. And that marble could be white or blue. And here the marble could be blue or white again. So if I list the possible outcomes, this top branch would represent that both marbles were blue. The second branch would represent that the first marble was blue and the second one was white, whereas the third branch would represent the first marble's white and the second is blue, and finally the last branch is when the event when the marbles are both white. Okay, now let's look at the probabilities of each. The probability of picking a blue marble, and I'll put this in green, would be 2 out of 6, because there are 2 blue marbles and 6 altogether, whereas the probability of picking a white marble would be 4 out of 6. Notice the sum of the probabilities is 6 out of 6, which is 1. Now, we put the marble back, so the jar still has 4 white and 2 blue marbles. These are 2 independent events. So, the probability of picking a blue marble is still 2 out of 6, and the probability of picking a white marble is 4 out of 6. And again, if the first marble was white, the probability of picking a blue is 2 out of 6, and the probability of picking a white is 4 out of 6. So if we wanted the probabilities of each of these outcomes, all right, I'll just put a little, another little column here so I don't go into the problem. So the probability that both marbles will be blue is 2/6 times 2/6, which gives us 4 out of 36. The probability that the first marble's blue and the second one is white would be 2/6 by 4/6, which is 8/36. The probability that the first is white and the second is blue would be 4/6 times 2/6, which is 8 out of 36. And finally, the probability that both are white would be 4/6 times 4/6, which gives us 16 out of 36. And notice that if we add all of these probabilities, 4 plus 8 is 12, plus 8 is 20, plus 16 is 36 out of 36, which means that when the probability is 1, the event must occur, like picking 2 marbles. That has to happen. Okay. Now, let's go back and answer these questions. We already answered them because we're using the counting principle of probability. So the probability that both are blue is 4 out of 36. The probability that both are white is 16 out of 36. The probability that both are the same color, okay, well, both would imply that we could have 2 blues or 2 whites. So let's write that down. We could have a blue or a white. And with the word or, we add these probabilities. So it's a probability of a blue plus the probability of a white. And that would give you 4 out of 36 plus 16 out of 36, which would give us 4 plus 16 out of 36, which gives us 20 out of 36. The probability that they're different colors, again, that's an or situation. We could have a blue-white or a white-blue. And if we add those probabilities, we have 8 over 36 plus 8 out of 36. That gives us 16 out of 36. And those would be the answer to the questions using the counting principle of probability. This problem is a problem called with replacement. And the older math books call these earn problems, but I've changed them to jar problems. All right, let's see what a problem would be without replacement. Let's take a look at number 3. In number 3, we have the same jar, 4 white marbles and 2 blue marbles. A marble is drawn but not put back into the jar, and then another marble is drawn. So this is a problem called without replacement. So the number of marbles in the jar change depending on what the first pick was. So let's make a diagram again, and I have plenty of room here, so I'll take advantage of it. So our diagram will look like a tree like before, where the first marble could be either a blue or a white. Okay, let's take a look at that. Now, when we pick the first marble, our jar looks like this: 4 white and 2 blue. So the probability of picking a blue marble is still 2 out of 6. The probability of picking a white marble is 4 out of 6. So everything looks the same so far. But suppose we picked a blue marble first. Then I could still pick a blue or a white again. But let's think about this. If the first marble is blue and we don't put it back, our jar would look like this. We have 4 white and 1 less blue marble. That would be 1 blue, because the first one's already blue. So depending on what the first marble was, the numbers in the jar change. So the probability of picking a blue again would be 1 out of 5, there's 1 blue and 5 marbles altogether, and the probability of picking a white would be 4 out of 5. That's because it's without replacement. Now, let's take a look at the next one. If the first marble was white, then, and we kept it, then our marbles would look like this. Oh, let me just get my black ink here going. Oh, where's my black? Okay, here we go. So this is the jar. It's not a very good jar, but it'll do. And we have, so if the first marble was the first marble was white, then we have 1 less white marble in the jar. That's 3 white, but the 2 blues stay. So notice that the jar has a different number of marbles depending on what the first marble was. So again, if the first marble was white, we could still pick a blue or a white again, and the outcome space would look the same. We would have 2 blues, a blue and a white and a blue, and the white and the white. And the probability, if the first marble was white, the probability that the second marble is blue would be 2 out of 5, because there are 2 blue marbles and 5 marbles altogether. And if the first marble was white, the probability that the second marble was white would be 3 out of 5. Oh no. Wait, is that right? Wait, if the first one was white, the second one was white, yes, it would be 3 out of 5. That's correct. Okay. Now, in this experiment, without replacement, they are not 2 independent outcomes, right? Because the probabilities of the second marble depended on what was drawn the first time. However, if we look at this as separate experiments, like suppose I have this jar, then the probability of drawing a blue and a white would be 2, 6, 4, 6. And if I had this jar, the probability of picking a blue and a white would be 1/5, 4/5. And again, this jar, the probability of picking a blue and a white are 2/5, 3/5 respectively. So even though these are 2 dependent events, we could think of these as separate individual experiments. So we can still multiply their probabilities. So the probability that we get a blue and then a blue without replacement would be 2 out of 6 times 1 out of 5, which gives us 2 out of 30. The probability of the first blue and the second white would be 2 out of 6 times 4 out of 6, 4 out of 5, excuse me. 4 out of 5, which would be 8 out of 30. The probability of a white and then a blue would be 4 out of 6 times 2 out of 5, which is again 8 out of 30. And the probability that both are white without replacement would be 4 out of 6 times 3 out of 5, which gives us 12 out of 30. And again, notice that when we add this column, the sum would be, 10, 18, and 12 is 30 out of 30. So the sum of the simple probabilities should always add up to 1. And now we have the problem now. We have the same questions, but we have different probabilities. So the probability that are both blue would be 2 out of 30. The probability both are white would be 12 out of 30. The probability that they're the same color, well, that's still blue, blue, white, white. Either one will do. So we add those 2 probabilities and we get 2 plus 12, which would give us 14 out of 30. And the probability that there would be different colors would be blue-white or white-blue. And again, either one is fine. So that would be 8 plus 8 out of 30. And again, this is a problem without replacement. Now, these probabilities, we don't really have to make a tree diagram for every problem. We could just reason it through. Because if we have 4 white and 2 blue, the probability of picking a blue is 2 out of 6. And if we already picked a blue, then that amount went down by 1 and we have 5 marbles left. So we could get these probabilities without a tree diagram. I just made a tree diagram so that we can see what's happening. Oh, I didn't answer part E, the probability that at least one is blue. Okay, I'm going to do part E here. So the probability of at least one blue, well, what are the outcomes? Well, they could both be blue, or the first is blue and the second is white, or the first is white and the second is blue. Or one of these outcomes would be okay. If I said to you, you'll win if you get at least one blue, then these are the outcomes that you'd be looking for, either BB, BW, or WB. But with OR, we add these. So we get the probability of both blue plus the probability of a blue and a white, and then a white, plus the probability of a white and then a blue. So if we add those together, we get 2 out of 30 plus 8 out of 30 plus 8 out of 30, and that would give us a total of, I think, 18 out of 30. Another way to do this same problem with at least is to look at the complement. So what would be the complement of getting at least one blue? The complement would be getting both white. So if we take 1 minus the probability of both white, we get 1 minus 12 out of 30, which again gives us 18 out of 30. But whichever way we do it, it works. It works. So let's take a look at another problem. All right, we're going to do number 4 on the sheet. Farmer Brown must wake up at sunrise to start his chores. Dressing in the dark, because I guess he wakes up really early, like 5 o'clock in the morning, he puts out 2 loose socks. There are 8 black socks and 6 navy blue socks in the drawer. So let's just imagine the situation. It's a dim, dark morning, and he opens up his drawer, and he takes out a sock, puts it on, and takes out another sock, not caring what he gets, because black is really close to navy blue, and who's going to check? So once he takes a sock and puts it on, he takes another sock. This is a problem without replacement. This is a problem without replacement because, well, he's not going to look in the drawer. I just want to try to make this interesting. So I'd like you to try answering these questions without a tree diagram. Do you think that the probability of pulling out 2 socks with matching colors is high? Because 8 black and 6 navy blue, you would think that the probability would be rather high. And how high would it be? Okay, well, think about that. Pause the video, try this problem without a tree diagram. If you must make a tree diagram, excuse me, feel free to do so, but you really don't have to. Okay, try it by yourselves. Okay, let's try it. So, the probability that both are black is that he picks 2 blacks one after the other. which is a matching pair. So the probability that the first is black would be 8 out of 14. But once he picks a black sock, there's one less sock in the drawer. So in the second time he picks a sock, it'll be out of 13. And how many black socks remain after he picked a black sock? One less black sock, which is 7/13. So we would multiply these two. I'll do that at the end with a calculator. Okay, now if the probability that they're both navy, well, the probability that the first is navy is 6 out of 14. There's 6 navy socks out of 14 total. But if he picked a navy sock the first time, there's one less navy sock. That would be 5. And there's one less sock in the drawer. That's 13. So let's just work out these probabilities quickly. And using my calculator, I found that the probability of both black would be 56 out of 182. And the probability that both are navy would be 30 out of 182. Now, this is what we're interested in. What's the probability that both are the same color? So here, what Farmer Brown is interested in is to get both black or both navy. But again, we add these probabilities. We have an or situation. Either one would be a matching pair and he's happy. So we would take 56 out of 182 and add it to 30 over 182, and our answer would be 86 out of 182. Let's see. If I change that back into a decimal, we get 0.472. That's pretty close to a half, I would say. So he has something really very close to a 50-50 chance of pulling out a matching pair of socks. Now, what's the probability that he has different colored socks? Well, again, like in the marble problem, we want the probability of a blue and a navy, or a probability of a navy and then a blue. So we would add these two. And let's look at those probabilities. So again, we have to be careful. The first time we pick the sock, it's out of 14 for both cases. Okay? But if the first one's blue, then, if the first one's black, then there is 8 possible ways. But once he picks a black sock, there's one less sock in the drawer. So this is true here too. But he still has 6 navy socks, because the navy socks are not touched. And then in the second probability, if the first sock is navy, that's 6 out of 14. But there's one less sock, but the black socks were not touched. So this is 8. So we get 48 plus 48 over 182. And the answer here is 96 out of 182. And if we change that into a decimal, the answer is about 0.518. So the probability of him picking 2 socks of different colors is a little bit more than a half. So he's more likely to pick a different colored socks than he is to pick a matching pair. But again, the probabilities are really very close to 1/2. So I thought that was an interesting problem. Let's try another. All right, now this problem is number 5 on the sheet. And I thought that I should give you a problem with a deck of cards, because this is where we see it. We see the counting principle for probability most often. Okay, so several players start playing a game with a full deck of 52 cards. Each player draws two cards at random, one at a time, without replacement. Okay. So, let's take a look at the questions. The probability that both cards are jacks, the probability that both cards are hearts, the probability that both cards are picture cards, the probability that the first card is a club and the second is a red card, or the probability that the first card is a 4 and the second card is 3, and the probability that they have the same suit. I left for extra credit a matching pair. That one is a little bit more challenging. So I want you to think of that for extra credit. Okay. So let's try these. Pause the video and come back to check. Okay. Let's look at the probability of getting both jacks. There's a 52 card deck. So the probability that the first is a jack would be 4 out of 52. But because we're not putting the jack back, there's one less jack. So for the second draw, if we want a jack, there's 3 possible jacks, and there's one less card. Okay, I'm going to leave my answer like that because I want to show you something in a few minutes. For the probability that both are hearts, well, there are 13 hearts because it's a suit, 13 ways to pick the first card. And then if the first card is a heart, there's one less heart, so there are 12 hearts we could pick up from in the second for the second card and one less card, so we have 51. Now, the probability that the first card is a club and the second is a red card. Now that one's interesting because the club is a suit, so there are 13 of them. So that's 13 out of 52. And then the second is a red card. So let's think about that carefully. Can a club be a red card? No, because I believe the club is a black card. So there are 26 cards in the deck, 26 of which are red. So there are 26 ways to pick a red card on the second pick because it does not affect the clubs or and there's one less card. So that's 51 ways. Okay, let's look at D. The probability that the first card is 4 and the second card is a 3. Well, how many 4s are in the deck? There are 4 of them, one of each suit, so that's 4 out of 52. Now we pick one less card, so the second denominator will always be 51. And the second card is a 3. Well, the second card, is a red 3, excuse me. That's very specific. Well, how many red 3s are there? Well, let's see. There are 4 3s and 2 are red, I believe. So that would be 2 out of 51. And the 2 red cards are red of diamonds and red of hearts. Now, the same suit is more complicated because notice that, all right, I'm going to write this down here. Okay, now what are the suits? Well, I've got a heart, or a diamond, or a spade, or a club. Okay, all right. Okay, that's good enough. All right. Now, In each suit, there are 13 cards. Since we have 13 times 4 is 52. So again, we're going to add these. So we're going to have the probability of the first heart and then the second heart, plus the probability of the first diamond and the second diamond. Okay, plus the probability of a spade, spade. Plus the probability of two clubs. Okay, all right. Now, the probability of picking a heart the first time would be 13 out of 52. But because there's one less heart, we have 12 out of 51. The same is true for diamonds. And the same is true for spades. And the same is true for the clubs. Okay. So we could express this answer as 4 times 13 out of 52 plus 13 out of 52 times 12 out of 51. Now, I didn't multiply these deliberately because I want to tie them in with permutations. Let's look at permutations. If you recall from the previous video, 4 factorial is 4 times 3 times 2 times 1. But 4p2 means that we've got 2 spots and we count 4 times 3. So all of these probabilities can be expressed in permutation notation. Let's look at it. In the very first one, in part A, we could write this as 4p2 over 52p2. The number of ways to arrange 2 cards from 4 and the number of ways to arrange 2 cards from 52. The same is true in the next one. This is 13p2 over 52p2. This one, we would have to express it as a product. This would be, all right, I'll put part C down here because it's hard to put it up there. 13 out of 52 would be 13p1 over 13p1 times 26p1 over 52p2. And in the last one, we're going to pick 1 card from 4 times, okay, now to pick the second card as a red 3, we're picking 1 card from 2 possible cards. And that's divided by 52p2. Okay, so this belongs with that. And this one belongs with C. And in the last one, we could write this as 4 times 13p2 over 52p2. And this 4, we will learn later, comes in with combinations. But I think it's easier just to list it this way. It would be easier this way. Okay, so that takes care of this problem. And now I wanted to do one more problem that I found from one of these old textbooks. So I found this problem in my notes back in my college years. Okay, and I'd like you to try it. We have 2 jars. Jar A has 5 red and 3 white marbles, and jar B has 2 red and 6 white marbles. If a marble is drawn from each jar, what is the probability that they are both of the same color? So I'd like you to copy this down and try it yourself. All right, so in this problem, we have to think, is this problem with or without replacement? Well, because we are drawing from two different jars, and the numbers are not affected no matter what marble we get in either jar, then this is a problem with, we would think of it as with replacement, but they are two independent events. So if we want the same color, we're looking at the probability that both are red or both are white. So we have to add these probabilities. So the probability that the first marble's red from jar A is 5 out of 8, and the marble is red from jar B is 2 out of 8. The probability that the marble is white from jar A is 3 out of 8, and the probability that the marble is white from jar B is 6 out of 8. So here we get 10 plus 18, which is 28 out of 64. Now this next one is a little bit more challenging. If we pick 2 marbles from each jar, what is the probability that all 4 will be the same color? Now here we've got a little bit of a mixture. This becomes a problem without replacement. So try this one and let's see what we get. Okay, so let's take a look at the answer. So if we want all 4 to be the same color, we want the probability of 4 R's or the probability of 4 W's. So the probability of picking a red marble from the first jar the first time is 5 out of 8. But if the first one is red, then we have 1 less red in the jar, and the probability of picking a red from that jar again is 4 out of 7. In jar B, the probability of picking a red would be 2 out of 8, and since there's 1 less red, the probability of picking a red again would be 1 out of 7. And the same is true with 4 whites. The probability of picking a white marble the first time from jar A is 3 out of 8, but because there's 1 less white marble, the second time would be 2 out of 7. And then in jar B, there's 6 white marbles out of 8 times and 1 less white marble, 5 over 7. And that is approximately, 220 over 3,136, which is approximately 0.070. Notice that probability is really very unlikely to happen. It's very close to 0. So to pick 4 marbles of matching color is highly unlikely in this particular experiment. Okay, so that takes care of our lesson on probability of 2 or more activities. And just to summarize, we introduced the counting principle for probability for independent events, for 2 independent events, but we could extend it to problems without replacement and with replacement. And we looked at several problems involving these. Okay, and there's so many other applications as we will see on our worksheets. Have a wonderful day. Bye.